Close your eyes and try to feel the floor beneath you. It feels solid, stationary, permanent. But the reality is far more violent. At this very second, you are hurtling through the vacuum of space at 230 kilometers per second. That is fast enough to circle the entire Earth in just 3 minutes. You have been doing this your entire life. Your parents did it. Every ancestor you've ever had, from the first nomadic tribes to the architects of the Great Wall, has been locked in this same silent trajectory. Every star you've ever wished upon, every planet in our solar system, and all 200 billion stars in the Milky Way are performing a vast, patient ballet around a single invisible center. For most of human history, we didn't even know it was there. We called the Milky Way a faint band of light, a diffuse cloud, or a river in the sky. By the early 1900s, we finally understood we lived in a spiral galaxy, but we assumed the center was just more stars. We thought it was a dense pool of starlight, heavier and brighter, but ultimately nothing special. We were wrong. Visual. The screen fades to absolute black. Only a faint shimmering orange ring begins to materialize in the center. Narrator. At the heart of our home sits a supermassive black hole, Sagittarius, a star. It is an object 4 million times the mass of our sun, crushed into a point of infinite density. But there is a secret about this invisible giant that most documentaries never tell you. We aren't actually looking at a black hole. We are looking at a phantom. Because of the speed limit of the universe, the speed of light, information has a delay. Sagittarius. A star is 26,000 light-years away. That means the light reaching our telescopes today left the galactic center 26,000 years ago. To understand the scale of that time gap, you have to realize that when those photons first began their journey toward us, modern human civilization didn't exist. Humans were living in the depths of the last ice age. We were small bands of hunter-gatherers huddled around firelight, using stone tools to survive a frozen world. Writing hadn't been invented. Agriculture was 15,000 years away. While we struggled to survive the cold, those photons were just beginning to pierce through the thick curtains of interstellar dust, racing toward a future they would never see. Narrator. This creates a profound information paradox that we are only just beginning to confront. The Sagittarius A star we photographed in 2022 is ancient history. It is a 26,000-year-old echo. If the black hole had suddenly flared into a roaring quasar this morning, or if it had finally begun devouring the surrounding star cluster in a feeding frenzy, we wouldn't know about it for another 260 centuries. We are effectively blind to the now. But why has this giant stayed so quiet for so long? Most outlier videos will tell you it's simply starved of gas. But the deep lore, the data hidden in our most obscure observations, suggests something far more mysterious. Scientists have observed that Sagittarius A star is a selective feeder. In 2014, a massive gas cloud named G2 swung right into the mouth of the beast, and the world held its breath, expecting a firework show of X-rays. And then, nothing happened. The black hole didn't eat it. This brings us to a massive lore gap that mainstream science is still debating. Is Sagittarius A star actually being shielded? Some theories suggest a dark matter spike, a dense, invisible scaffold of dark matter that acts as a gravitational buffer, subtly warping the trajectories of everything that comes near the core. This invisible hand might be the reason our black hole is a quiet tyrant rather than a cosmic predator. Visual, abstract 3D visualization of dark matter as glowing purple filaments weaving around the orange event horizon. Narrator. But the mystery goes even deeper than the environment. It goes into the very fabric of the black hole itself. While we see a shadow in our radio images, theoretical physics is grappling with the possibility that there is no singularity inside. Instead, we might be orbiting a fuzzball, a tangled, vibrating nest of fundamental strings of energy that doesn't just swallow information, but preserves it in a way our current math can't comprehend. For centuries, the center of our galaxy was hidden behind a wall of dust. Astronomers like William Herschel tried to count the stars to find the center, but they were staring at a curtain they couldn't pull back. It wasn't until the 1970s, when we began to use radio eyes that could see through the soot and smoke of space, that we heard the heartbeat of the giant for the first time. We found a compact, unmoving source of energy that we named with an atomic physics symbol, the asterisk, Sagittarius A star, an excited state, a mark on the map that represented a hole in the universe. Visual, a fast-paced montage of radio dishes turning in unison, flickering data screens, and the blue-white star S2 whipping around an invisible point. Narrator, in this documentary, we aren't just going to show you the orange donut you've seen 1,000 times. We are going to step into the 26,000-year-old shadow of a ghost. We will explore the invisible dark matter architecture that anchors our galaxy, the magnetic mayhem that chokes the black hole's food supply, and the terrifying possibility that our own universe is just a seed growing inside the very monster we are orbiting right now. You've been moving your entire life. It's time you finally saw what you're running toward. This is the story of the invisible giant. If you travel far enough away from the light pollution of our cities, you'll see it. A pale, ghostly river of light flowing across the night. For thousands of years, this was the most beautiful thing the human eye could perceive. Ancient Greeks called it a path of milk. Indigenous Australians saw an emu in the sky. But to modern astronomers, for a very long time, this beautiful band of light was something else entirely. It was a crime scene, and the evidence was hidden behind a wall. Whenever we turned our most powerful visible light telescopes toward the heart of our galaxy, we ran into a frustrating, impenetrable darkness. It wasn't an absence of stars. It was a presence of smoke. Visual, a 3D animation diving into a dark nebula. We see tiny, jagged particles of carbon, ice, and rock floating in the void. Narrator, between us and the galactic center lies a colossal curtain of interstellar dust. These aren't just dust bunnies like you find under your bed. These are microscopic grains of carbon, silicates, and rock, the soot and ash of dead stars. Because these particles are roughly the same size as the wavelengths of visible light, they act like a cosmic smokescreen. They scatter and absorb every photon trying to make its way to Earth. This wall of dust is so thick that it blocks 99.9% of the visible light from the galactic core. For centuries, we were essentially looking at a closed door, trying to guess what was happening in the room behind it. Visual, a portrait of William Herschel next to his hand-drawn map of the Milky Way, a strange, jagged shape with the sun at the center. Narrator, this led to the greatest sun-centric delusion in history. In the late 1700s, the great astronomer William Herschel tried to map the shape of the Milky Way by simply counting every star he could see. He looked in every direction, counted the points of light, and concluded that the sun was at the very center of the universe. Why? Because in every direction he looked, the stars eventually thinned out and stopped. He didn't realize he wasn't seeing the edge of the galaxy. He was just seeing the edge of the smoke. He was like a man in a thick fog who believes the world only extends 50 feet in every direction, because that's where his vision fails. We were blind to the true nature of our home, until we learned to see in a language that dust couldn't stop. Visual, the screen shifts into an X-ray/thermal view. The dark clouds suddenly become transparent, revealing a frantic, glowing hive of activity beneath. Narrator, the breakthrough didn't come from a mountaintop observatory. It came from a backyard in New Jersey and a man who wasn't even an astronomer. In the early 1930s, a young engineer named Carl Jansky was working for Bell Telephone Laboratories. He wasn't looking for black holes, he was looking for static. Specifically, the static that was interfering with long-distance radio calls across the Atlantic. To find the source, he built a strange, rotating antenna that looked more like a piece of farm equipment than a telescope. People called it the merry-go-round. Visual, archival footage or a recreation of Jansky's merry-go-round antenna rotating slowly on its wooden wheels. Narrator: Jansky found the lightning, he found the thunderstorms, but he also found a steady rhythmic hiss that peaked once every 24 hours. Except, it wasn't exactly 24 hours. It arrived 4 minutes earlier every day. That was the eureka moment. That 4-minute shift meant the signal wasn't coming from Earth, and it wasn't coming from the sun. It was tied to the rotation of the stars. Jansky had accidentally heard the center of our galaxy. The radio waves, which have much longer wavelengths than visible light, were sliding right past the grains of dust like a surfer riding over small ripples in the water. The wall of dust was finally transparent. Visual, a transition from Jansky's crude antenna to a modern massive radio dish like ALMA in the Atacama Desert. Narrator: but the true nature of the beast remained elusive. It took another few decades and a high-resolution radio scan in 1974 for astronomers Bruce Ballack and Robert Brown to zero in on a single compact point at the heart of the radio noise. They found something that didn't spread out like a nebula and didn't flicker like a normal star. It was a bright, concentrated engine of energy. To name it, they looked to the constellation Sagittarius, where the signal lived. It was the first and brightest source in that region, so they called it Sagittarius A. But they added something else, a mark of distinction, an asterisk. Appears on screen in a bold scientific font. The asterisk glows with a faint orange light. Narrator: in the lore vault of scientific history, this asterisk is more than just a footnote. Ballack and Brown borrowed the symbol from atomic physics. In that field, an asterisk denotes an excited state, an atom with more energy than usual, vibrating on the edge of something extreme. It was a prophetic choice. Sagittarius A star was indeed in an excited state, but not in a way they could yet prove. As the radio images got sharper, the mystery grew deeper. This source was too bright to be a single star, yet it was unmoving. In a galaxy where everything is drifting and spinning, this object sat perfectly still at the gravitational dead center of the Milky Way. It was the anchor. Visual: a 3D model of the galactic core. Stars are represented by streaks of light, all spiraling around a central empty hole where the radio signal is coming from. Narrator: but here is where the story takes a turn into the unanswered mystery that we discussed in the beginning. Most documentaries stop here and say, "We found the radio signal, so we found the black hole." But the data was screaming that something was wrong. When we looked at other galaxies, their centers were roaring with energy, blazing quasars that could be seen from the other side of the universe. But our giant Sagittarius A star was quiet. Too quiet. It was like finding a dormant volcano in the middle of a crowded city. Why was it refusing to eat? Why was this invisible giant holding back? As we peeled back the wall of dust, we didn't just find a black hole. We found a puzzle. We found a supermassive object that seemed to be actively deflecting the very gas and dust we used to find it. We had pierced the veil, but the ghost inside was staring back at us with a secret we weren't ready to hear. To find the truth, we had to stop listening to the radio and start watching the stars perform a dance that should have been impossible. Visual: a final shot of the glowing orange asterisk against a pitch-black background, slowly being surrounded by the fast-moving blue streaks of the S stars. Narrator: the curtain was up, the stage was set, and in Chapter 3, we are going to watch the most violent ballet in the cosmos, a split screen of two of the most isolated places on Earth. On one side, the oxygen-thin, frozen summit of Mauna Kea in Hawaii. On the other, the bone-dry, Mars-like landscape of the Atacama Desert in Chile. In both locations, massive silver domes begin to open, their giant glass eyes reflecting the glittering core of the Milky Way. Narrator: if you want to find a ghost, you have to be patient. You have to sit in the dark for a long time and wait for something, anything, to move in a way that defies the laws of nature. In the early 1990s, two rival teams of astronomers, led by Andrea Ghez and Reinhard Genzel, decided to do exactly that. They weren't looking for distant galaxies or exploding supernovae. They were stalking a shadow at the very center of our own home. Using the Keck Observatory and the Very Large Telescope, they focused on a tiny, unremarkable patch of sky within the constellation Sagittarius, a region no larger than a grain of sand held at arm's length. But what they found was a cosmic crime scene, visual, a series of grainy, time-lapse infrared images. Dozens of blue and white dots are seen moving in chaotic, rapid circles around a central crosshair where there is only blackness. Narrator. In the suburbs of the galaxy where our sun lives, stars move with a stately, predictable grace. It takes our sun 230 million years to complete a single orbit around the galactic center. But as Ghez and Genzel's teams looked closer at the heart of the Milky Way, they saw a stellar ballet that was far more violent. They found a group of stars, now known as the S stars, that were performing a high-speed dance around nothing. These stars weren't drifting. They were whipping. They were racing through space at thousands of kilometers per second, locked in tight, elliptical orbits around a point that was absolutely, terrifyingly dark. One star in particular, a blue-white giant called S2, became the key to unlocking the entire mystery. Visual, a high-fidelity 3D animation of the star S2. It is a massive, glowing blue orb, but it looks fragile compared to the invisible gravity while it is approaching. As it nears the center, it begins to stretch and glow brighter. Narrator. S2 is a star that shouldn't make sense. It completes a full orbit around the galactic center every 16 years. Think about that. While our sun takes 230 million years, S2 does it in less time than it takes a human to finish high school. At its closest approach, its periapsis, S2 screams past the center at a distance of only 17 light hours. For context, that is roughly 4 times the distance from our sun to Neptune. But S2 isn't orbiting a sun. It is orbiting a ghost. At that distance, the star accelerates to nearly 3% the speed of light, roughly 7,000 kilometers per second. That is fast enough to travel from the Earth to the Moon in less than 60 seconds. Visual. The animation of S2 reaches its closest point to the center. The star appears to wobble, and its light shifts from blue to red. Narrator. As S2 reached this extreme point, the teams observed something that changed physics forever. They saw gravitational redshift. As the star fought to escape the intense gravity of the center, its light was literally stretched. The waves of light were pulled apart by the curvature of space-time itself, turning the star's blue light redder as it climbed out of the gravity well. This was the smoking gun. To make a star move that fast, in an orbit that tight, there has to be something with a mass of 4 million suns packed into a space smaller than our solar system. If that mass were made of stars, they would be so crowded they would have long ago collapsed into each other. If it were a cloud of gas, it would have been blown away by its own heat. There is only one object in the known universe that can be that heavy and that small, a supermassive black hole. Visual. The screen darkens. A new layer of visualization appears, a shimmering, needle-like density of purple light that surrounds the black hole, even denser than the stars themselves. Narrator. But here is where the stellar ballet reveals a lore gap that most documentaries completely ignore. If you look at the math, there is a lingering shadow in the data. This is the mystery of the dark matter spike. Standard physics tells us that the gravity of Sagittarius A star is what controls S2. But some theorists believe the black hole isn't alone. Over billions of years, the intense gravity of the center may have pulled in a spike of dark matter, an invisible scaffold of high-density particles that surrounds the event horizon. This spike would act like a hidden hand, subtly warping the orbits of the S stars in ways that ordinary gravity cannot explain. If this spike exists, it means the 4 million solar masses we've measured might not all be the black hole itself. A fraction of that mass could be the invisible architecture of the galaxy itself, a dark shroud that we are only just beginning to detect by watching the wobble of stars like S2. Visual, a close-up of the star S2 as it moves away from the center. It looks slightly battered, its gases trailing behind it. Narrator, and then there is the S-star paradox. S2 and its companions are young stars. They are blue, massive, and only a few million years old. But they are living in a graveyard. The environment around Sagittarius A is a chaotic storm of radiation and tidal forces that should make it impossible for new stars to form. How did they get there? Did they migrate from the outer arms like cosmic refugees? Or did they form in situ, born from a disk of gas that was shredded and compressed by the black hole's gravity? For decades, we watched these stars perform their impossible dance. We followed S2 through its full 16-year loop in 2002, and again in 2018, confirming Einstein's predictions with every pass. We had mapped the gravity, we had measured the mass, we had heard the radio hiss, but we still hadn't seen the face of the monster. We were like detectives who had found the footprints, measured the weight of the intruder, and even heard him breathing in the dark. But we hadn't turned on the lights. That was about to change. Visual, a fast montage of radio telescope dishes across the planet, from the South Pole to the Alps, all swiveling in perfect unison to point toward the same coordinate. Narrator, to see the unseeable, we would need a telescope the size of the entire planet. We were about to take a photograph that shouldn't exist. If you look across the deep trenches of the universe, you will find monsters that defy description. Active galaxies and quasars, powered by black holes billions of times more massive than our own, are the brightest beacons in existence. They are so greedy, so voracious, that they outshine the combined light of every star in their host galaxy. They are cosmic engines running at 100% throttle, devouring entire solar systems like snacks. And then, there is our black hole, Sagittarius. A star is a paradox. It has the mass, it has the gravity, and it is surrounded by a dense, bustling city of gas and stars. The table is set. The feast is laid out. And yet, for some reason, the giant has its mouth closed. In the world of supermassive black holes, Sagittarius A star is performing a fasting act that has stumped astronomers for decades. It is nearly 1 billion times fainter than it technically should be. Most of the time, it's quiet, starved, a sleeping titan that refuses to wake up. But in 2014, we thought we were finally going to see the monster bite. Visual, a high-contrast infrared view of the galactic center. A small, glowing red smudge labeled G2 is seen heading directly toward the central black crosshair. Narrator. In 2011, astronomers discovered a mysterious object named G2. It appeared to be a massive cloud of hydrogen gas, 3 times the mass of the Earth, hurtling through the galactic core. Its trajectory was a straight line toward the event horizon. This was the feast of the century. The scientific community was electric with anticipation. Every major telescope on Earth and in space, Chandra, XMM Newton, the VLT, swiveled to watch the encounter. We expected the black hole to shred the cloud, creating a spectacular display of X-ray fireworks as the gas was superheated and swallowed. We expected to finally see Sagittarius a star roar. But 2014 came and went. The cloud made its closest approach, swinging within a hair's breadth of the point of no return. And then, nothing happened. Visual. The G2 cloud passes the black hole. Instead of being swallowed, it merely stretches out like a piece of cosmic taffy and continues its orbit, emerging on the other side mostly intact. Narrator. The giant refused to eat. The monster didn't even flinch. G2 survived its encounter with the most powerful object in our galaxy and continued on its way, slightly stretched but largely unconsumed. This brings us to one of the most profound mysteries in the lore vault of the Milky Way. Why is our black hole such a picky eater? The answer lies in a concept that most documentaries overlook, a strange state of physics called a radiatively inefficient accretion flow. To understand this, forget everything you know about black holes being cosmic vacuum cleaners. In reality, Sagittarius A star is more like a cosmic blender with the lid off. Visual, an animation of a bonfire. One person is trying to stack logs neatly to create a bright flame, but a high-powered fan is blowing the wood away before it can even touch the fire. Narrator. Imagine trying to build a bonfire. If you stack the logs tightly and light them, you get a bright, intense, efficient flame. That is a quasar. But around Sagittarius, a star, the logs, the gas and dust, are scattered loosely in a wide, chaotic circle. Because the environment is so turbulent, the material never gets the chance to settle into a neat, glowing disk. Instead, it swirls around in a hot, thin, disorganized mess. But here is the real secret: Sagittarius. A star is actively pushing its food away. As matter tries to fall inward, it gets caught in a violent tug-of-war. The black hole's gravity is pulling, yes, but the intense heat and twisting magnetic fields are pushing back. This creates a cosmic shield. Data suggests that 99% of the gas that tries to fall into Sagittarius A star is actually blown back out into space by powerful winds and turbulence before it ever reaches the event horizon. Only a tiny, starving trickle, less than 1%, actually makes the final plunge, showing them acting like a fence that deflects incoming particles. Narrator. This selective feeding anomaly is why the G2 cloud survived. Some theorists now believe that G2 wasn't just a gas cloud at all, but a dusty star, a central object hidden inside a protective cocoon of gas. The black hole's gravity couldn't strip the star's core, and its inefficient feeding habits meant it wasn't powerful enough to swallow the whole package in one go. But don't let the quietness fool you. Just because the giant is sleeping doesn't mean it's harmless. Even in this subdued state, Sagittarius A star occasionally lets out a stomach growl. We see these as sudden, unpredictable flares in X-ray and infrared light, bursts of energy that can outshine the black hole's baseline brightness by 30 or 40 times in a matter of minutes. These flares are the fingerprints of magnetic reconnection. Think of it like a rubber band being stretched until it snaps. Near the event horizon, magnetic field lines become so tangled and stressed that they eventually break and rearrange themselves, releasing a titanic burst of energy and accelerating particles to near-light speeds. Visual. A flash of X-ray light erupting from the orange ring, sending a ripple across the surrounding gas. Narrator. These flares are brief glimpses into the monster's true potential. They remind us that the quiet tyrant is only quiet because of a delicate temporary balance between gravity and magnetism. But what if that balance shifted? Evidence from X-ray echoes bouncing off distant gas clouds suggests that only a few hundred years ago, our black hole was much, much brighter. We are living in a rare lull, a moment of cosmic silence in a history that has likely been much louder and more violent. The fact that we can study the black hole in this rest state is a gift to science. Because the giant has its mouth closed, we can see past the glare of the feast. We can look directly at the shadow. We can study the magnetic architecture that would be invisible if it were buried under a blazing accretion disk. But now that we've seen the face and understood the diet of the ghost, we have to ask the most terrifying question of all. What happens if you go inside? What happens when the selective feeder finally stops being selective and you become the one thing it cannot push away? Visual. The camera begins a slow, inevitable crawl toward the black center of the event horizon. The stars begin to warp and stretch into long, thin needles of light. Narrator. We have mapped the orbits. We have seen the shadow. We have analyzed the flares. Now, it's time to cross the line. In Chapter 6, we are entering the point of no return. We are going to explore the architecture of the event horizon, the place where escape is no longer a word that exists in the language of physics. If you look across the deep trenches of the universe, you will find monsters that defy description. Active galaxies and quasars, powered by black holes billions of times more massive than our own, are the brightest beacons in existence. They are so greedy, so voracious, that they outshine the combined light of every star in their host galaxy. They are cosmic engines running at 100% throttle, devouring entire solar systems like snacks. And then, there is our black hole. Sagittarius A star is a paradox. It has the mass, it has the gravity, and it is surrounded by a dense, bustling city of gas and stars. The table is set. The feast is laid out. And yet, for some reason, the giant has its mouth closed. In the world of supermassive black holes, Sagittarius A star is performing a fasting act that has stumped astronomers for decades. It is nearly 1 billion times fainter than it technically should be. Most of the time, it's quiet, starved, a sleeping titan that refuses to wake up. But in 2014, we thought we were finally going to see the monster bite. Visual, a high-contrast infrared view of the galactic center. A small glowing red smudge labeled G2 is seen heading directly toward the central black crosshair. Narrator. In 2011, astronomers discovered a mysterious object named G2. It appeared to be a massive cloud of hydrogen gas, 3 times the mass of the Earth, hurtling through the galactic core. Its trajectory was a straight line toward the event horizon. This was the feast of the century. The scientific community was electric with anticipation. Every major telescope on Earth and in space, Chandra, XMM Newton, the VLT, swiveled to watch the encounter. We expected the black hole to shred the cloud, creating a spectacular display of X-ray fireworks as the gas was superheated and swallowed. We expected to finally see Sagittarius A star roar. But 2014 came and went. The cloud made its closest approach, swinging within a hair's breadth of the point of no return. And then, nothing happened. Visual. The G2 cloud passes the black hole. Instead of being swallowed, it merely stretches out like a piece of cosmic taffy and continues its orbit, emerging on the other side, mostly intact. Narrator. The giant refused to eat. The monster didn't even flinch. G2 survived its encounter with the most powerful object in our galaxy and continued on its way, slightly stretched, but largely unconsumed. This brings us to one of the most profound mysteries in the lore vault of the Milky Way. Why is our black hole such a picky eater? The answer lies in a concept that most documentaries overlook, a strange state of physics called a radiatively inefficient accretion flow. To understand this, forget everything you know about black holes being cosmic vacuum cleaners. In reality, Sagittarius A star is more like a cosmic blender with the lid off. Visual. An animation of a bonfire. One person is trying to stack logs neatly to create a bright flame, but a high-powered fan is blowing the wood away before it can even touch the fire. Narrator. Imagine trying to build a bonfire. If you stack the logs tightly and light them, you get a bright, intense, efficient flame. That is a quasar. But around Sagittarius, a star, the logs, the gas and dust, are scattered loosely in a wide, chaotic circle. Because the environment is so turbulent, the material never gets the chance to settle into a neat, glowing disk. Instead, it swirls around in a hot, thin, disorganized mess. But here is the real secret. Sagittarius, a star, is actively pushing its food away. As matter tries to fall inward, it gets caught in a violent tug of war. The black hole's gravity is pulling, yes, but the intense heat and twisting magnetic fields are pushing back. This creates a cosmic shield. Data suggests that 99% of the gas that tries to fall into Sagittarius A star is actually blown back out into space by powerful winds and turbulence before it ever reaches the event horizon. Only a tiny starving trickle, less than 1%, actually makes the final plunge, showing them acting like a fence that deflects incoming particles. Narrator. This selective feeding anomaly is why the G2 cloud survived. Some theorists now believe that G2 wasn't just a gas cloud at all, but a dusty star, a central object hidden inside a protective cocoon of gas. The black hole's gravity couldn't strip the star's core, and its inefficient feeding habits meant it wasn't powerful enough to swallow the whole package in one go. But don't let the quietness fool you. Just because the giant is sleeping doesn't mean it's harmless. Even in this subdued state, Sagittarius A star occasionally lets out a stomach growl. We see these as sudden, unpredictable flares in X-ray and infrared light, bursts of energy that can outshine the black hole's baseline brightness by 30 or 40 times in a matter of minutes. These flares are the fingerprints of magnetic reconnection. Think of it like a rubber band being stretched until it snaps. Near the event horizon, magnetic field lines become so tangled and stressed that they eventually break and rearrange themselves, releasing a titanic burst of energy and accelerating particles to near-light speeds. Visual, a flash of X-ray light erupting from the orange ring, sending a ripple across the surrounding gas. Narrator. These flares are brief glimpses into the monster's true potential. They remind us that the quiet tyrant is only quiet because of a delicate temporary balance between gravity and magnetism. But what if that balance shifted? Evidence from X-ray echoes bouncing off distant gas clouds suggests that only a few hundred years ago, our black hole was much, much brighter. We are living in a rare lull, a moment of cosmic silence in a history that has likely been much louder and more violent. The fact that we can study the black hole in this rest state is a gift to science. Because the giant has its mouth closed, we can see past the glare of the feast. We can look directly at the shadow. We can study the magnetic architecture that would be invisible if it were buried under a blazing accretion disk. But now that we've seen the face and understood the diet of the ghost, we have to ask the most terrifying question of all. What happens if you go inside? What happens when the selective feeder finally stops being selective and you become the one thing it cannot push away? Visual. The camera begins a slow, inevitable crawl toward the black center of the event horizon. The stars begin to warp and stretch into long, thin needles of light. Narrator. We have mapped the orbits. We have seen the shadow. We have analyzed the flares. Now, it's time to cross the line. In Chapter 6, we are entering the point of no return. We are going to explore the architecture of the event horizon, the place where escape is no longer a word that exists in the language of physics. We have spent the last 6 chapters standing on the shore of a cosmic ocean, watching the waves and the storms from a safe distance. We have mapped the stellar ballet and survived the magnetic mayhem, but every explorer knows that you cannot truly understand the abyss until you step into it. We are now crossing the most terrifying boundary in the universe, the event horizon. To the human mind, a horizon is usually a suggestion, a line where the Earth meets the sky that recedes as you move toward it. But in the heart of the Milky Way, the horizon is a hard, mathematical fact. It is a one-way membrane in the fabric of reality. For Sagittarius A star, this point of no return is a sphere roughly 24 million kilometers across. If you were to lay 17 of our suns side by side, they would just barely span the diameter of this dark kingdom. But as we cross this line, we must abandon our everyday ideas of space and solid objects. The event horizon isn't a shell. It isn't a surface you could touch or a wall of fire that would incinerate you on impact. It is simply a coordinate in space where escape stops being a direction. Visual. An animation showing a grid of space-time. As the probe approaches the black hole, the grid lines don't just bend. They begin to flow downward, like water disappearing into a drain. Narrator. Think of it like a river. Far upstream, you can swim against the current. As you get closer to a waterfall, the current speeds up. The event horizon is the specific point where the river of space is flowing inward faster than the speed of light. Since nothing in our universe can travel faster than light, once you pass that threshold, no amount of rocket power, no engine, and no signal can ever push you back out. You haven't just entered a place, you have entered a trap of geometry. But there is a haunting paradox to this crossing. a mystery of perspective that Einstein called gravitational time dilation. If you were on this probe, looking at your watch as you crossed the horizon, you wouldn't feel anything special. You would simply drift into the darkness, the stars of the Milky Way still visible behind you, though warped and blue-shifted into strange, brilliant arcs. However, if we were watching you from the safety of Earth, we would see something entirely different. We would see a ghost. Visual. The probe appears to slow down as it hits the edge of the darkness. Its light turns deep red, then fades into a faint, frozen silhouette that never actually disappears. Narrator. As the probe approaches the horizon, the extreme gravity of Sagittarius A star warps the light coming from it. To us, back on Earth, the probe would appear to slow down. The seconds on its clock would stretch into minutes, then hours, then centuries. The light from the probe would shift into the deep infrared, then into radio waves, becoming redder and dimmer. Because space-time is so warped, we would never actually see the probe cross the line. Instead, its image would seem to freeze at the edge of the abyss, becoming a faint, red-shifted phantom that lingers forever. This is one of the deepest lore gaps in our understanding of black holes. The universe literally refuses to let us witness the final plunge. We are left watching 26,000-year-old echoes of objects that, from their own perspective, were destroyed eons ago. Visual. The camera dives through the frozen image of the probe, entering the absolute blackness inside the event horizon. The outside world, the Milky Way, shrinks into a tiny, brilliant circle of light directly above. Narrator. Now, we are inside. We are in the sealed box that can never be opened. Standard physics textbooks will tell you what happens next. They will speak of spaghettification, the process where the gravity at your feet is so much stronger than the gravity at your head that you are stretched into a thin atomic thread. They will tell you that you are moving toward the singularity, a point of infinite density at the center where all the mass of those 4 million suns is crushed into a space of zero volume. But infinity is not a physical description. It is a sign that our math has failed. It is a lore gap so large that it threatens to consume the foundations of science itself. This is where we must look at the more obscure high-retention theories hidden in the vaults of modern physics. What if there is no singularity? Visual. Inside the darkness, the singularity is replaced by a vibrating, tangled nest of glowing neon threads, the fuzzball. Narrator. Some researchers, drawing from string theory, propose the fuzzball hypothesis. They suggest that Sagittarius A star isn't an empty void with a point of mass at the center. Instead, the entire interior is a tangled, vibrating nest of fundamental strings of energy. In this view, the event horizon isn't a mathematical line, but the physical surface of this fuzzball. This leads us to the information paradox, the ultimate battle between Einstein and quantum mechanics. Quantum physics insists that information, the data that makes up you, me, and everything we see, can never be truly destroyed. But Einstein's theory suggests that once something falls into a black hole, it is gone. If you throw a book into Sagittarius A star, does the information in those pages vanish? Or is it somehow encoded onto the surface of the horizon, like a 2D hologram of a 3D object? This is the dark shadow of our understanding. If information is destroyed, then the laws of the universe are not consistent. If it is preserved, then our idea of interior space is an illusion. Visual. The fuzzball begins to expand, and within its glowing threads we see the faint, ghostly outlines of other stars and galaxies. Narrator. But there is an even wilder possibility, a theory that suggests we don't need to travel 26,000 light-years to see the inside of a black hole, because we might already be there. This is the seed universe hypothesis. Some cosmologists propose that when a supermassive black hole like Sagittarius A star forms, the extreme density doesn't just crush matter into nothingness. Instead, it triggers a big bang on the other side. The interior of the black hole becomes a brand new, expanding universe, invisible to the parent galaxy but vast and infinite to those inside it. Under this model, black holes are the reproductive organs of the cosmos. Our own Big Bang might have been the moment a 4 million solar mass star in a parent universe collapsed into a black hole, giving birth to the space-time we now inhabit. We are the children of a giant we can never see. We see the dark matter spike filaments from the previous chapters weaving through the event horizon, anchoring the entire structure. Narrator: as we drift toward what our current math calls the singularity, we realize that Sagittarius A is more than just a graveyard for stars. It is the boundary where our reality ends and something else begins. Whether it is a nest of strings, a portal to a new universe, or a holographic storage device for the history of the galaxy, the invisible giant remains the ultimate gatekeeper. We have looked into the mouth of the monster. We have explored the geometry of the point of no return. But there is one more invisible force we haven't fully reckoned with. Because while we have been focusing on the black hole, we have ignored the ghost scaffold that holds it in place. Beyond the horizon, beyond the magnetic fields, lies a hidden architecture that weighs more than the black hole itself. Visual. The camera pulls back rapidly, escaping the darkness and moving out into the cold, purple-shrouded regions of the galactic core. Narrator: in Chapter 8, we are going to hunt for the hidden hand of the Milky Way. We are going to explore the dark matter spike, the invisible scaffold that wraps around Sagittarius A and determines the fate of every star in our galaxy. We have spent this journey looking at the things that glow, the orange ring of the event horizon, the blue-white fire of the S-stars, and the X-ray flashes of magnetic storms. But there is a secret to our galaxy that is far heavier, far older, and entirely invisible. To understand Sagittarius A star, you have to understand that the invisible giant isn't actually alone. It is wrapped in a shroud, a hidden scaffold that dictates the fate of every star in the Milky Way. This is the mystery of the dark matter spike. Standard astronomy tells us that Sagittarius A star is 4 million times the mass of the Sun. We know this because of the stellar ballet we watched in Chapter 3. We saw the star S2 whip around the center and used its orbit to weigh the monster. But as our measurements have become more precise, down to 1,000th of a second of arc, the width of a human hair from miles away, a strange ghost has appeared in the data. The math is starting to suggest that the gravity at the center of our galaxy is just a little bit different than it should be. And the reason might be that we aren't just orbiting a black hole. We are orbiting an invisible mountain. Visual, a wide shot of the Milky Way galaxy. The visible galaxy of stars fades, revealing a colossal fuzzy sphere of gray mist surrounding it, the dark matter halo. Narrator: most of the matter in our universe is dark. It doesn't emit light. It doesn't reflect it. And it doesn't absorb it. It passes through you, the Earth, and the Sun like a ghost through a wall. We only know it exists because its gravity holds galaxies together. Without this invisible glue, the Milky Way would fly apart like a spinning carousel that isn't bolted to the floor. Usually, dark matter is spread out in a puffy halo, thousands of light years across. It is diffuse. It is gentle. But at the center of the galaxy, the rules of the neighborhood change. When a supermassive black hole forms and grows over billions of years, it acts like a cosmic drain. As it pulls in gas and stars, it also pulls in the dark matter halo. But because dark matter doesn't interact with itself or lose energy by radiating heat, it can't just fall into the black hole and disappear like a gas cloud. Instead, it gets compressed. It gets packed into a dense, needle-like concentration. In the lore of theoretical physics, this is called a dark matter spike. Visual, a 3D simulation of the galactic center. The stars are moving, but we see a shimmering aura of purple light around the black hole that gets denser and sharper the closer it gets to the event horizon. Narrator: this spike is the hidden scaffold of the Milky Way. It is a region where the density of dark matter becomes so extreme that it may actually outweigh the stars themselves in the innermost regions of the galaxy. Think about what this means for our understanding of Sagittarius A star. If this spike exists, the invisible giant is actually a dual object. It is a black hole inside a dark matter shell. And this shell acts as a gravitational hidden hand that influences everything we see. This brings us to a massive lore gap that mainstream documentaries often ignore: the precession paradox. Einstein's general relativity makes a very specific prediction about how the star S2 should move. Because the black hole warps space, the star's orbit shouldn't be a perfect closed loop. It should precess or shift slightly with every orbit, drawing a shape like a cosmic spirograph. In 2018, we measured this precession, and it matched Einstein's math perfectly. But there's a catch. If there is a dense spike of dark matter surrounding the black hole, that extra mass should change the shape of the gravity. It should make the star S2 move in a way that Einstein's equations, based only on a point mass black hole, cannot account for. Visual. A diagram showing two orbits for the star S2. One is a solid blue line, Einstein's prediction. The other is a flickering red line that deviates slightly, the dark matter influence. Narrator. The fact that we haven't seen a massive deviation yet tells us two things. Either the dark matter spike is much smaller than we thought, or, and this is the new information that is currently haunting the halls of UCLA and the Max Planck Institute, the dark matter might be annihilating itself. If dark matter particles are their own antiparticles, then in the extreme density of the spike, they would be constantly colliding and exploding into pure energy. This annihilation would act as a limiter, preventing the spike from becoming too heavy. But there's another possibility, one that challenges the very existence of the black hole itself. Some researchers have proposed the dark shadow theory. They ask, what if the object at the center isn't a black hole at all? What if it is a boson star, a hypothetical ultra-dense ball of dark matter that is so compact it mimics the gravity of a black hole? Visual, a comparison between a traditional black hole, a hole in space, and a boson star, a solid, glowing sphere of exotic dark particles. Narrator. To a distant star like S2, a 4 million solar mass boson star and a 4 million solar mass black hole feel exactly the same. They both pull with the same weight. But the boson star wouldn't have an event horizon. It would have a fuzzy surface. The image from the Event Horizon Telescope in 2022 seemed to put this theory to rest. We saw the shadow, the dark silhouette where light is swallowed, but even that shadow has a margin of error. The lore vault suggests that a sufficiently dense dark matter core could still produce a shadow-like region by bending light so severely that it creates a dark central void. Why does this matter to you? Because the stability of your life depends on this invisible scaffold. Visual. The camera pulls back to show the entire spiral arm of the Milky Way where our solar system sits. Narrator. The dark matter spike isn't just a local curiosity. It is the anchor's anchor. It provides the gravitational depth needed to keep the galactic bulge stable over billions of years. If the dark matter spike weren't there, the orbits of the stars in the center would be far more chaotic. The stellar ballet would be a stellar riot. This invisible influence may also explain why our giant is so quiet. We talked in Chapter 5 about how Sagittarius A star pushes its food away. Some theoretical models suggest the dark matter spike acts as a gravitational buffer. It alters the viscosity of the space around the black hole, making it harder for gas clouds to settle into a feeding disk. The invisible giant might be a picky eater because its dark matter scaffold is literally standing in the way of the feast. Visual, a slow, dramatic zoom in on the dark center. The purple filaments of the spike are now seen vibrating, sending ripples out through the surrounding space. Narrator. We are orbiting an object that is part black hole, part magnetic storm, and part dark matter mountain. We have seen the fingerprints of its mass. We have heard its radio hiss. We have even mapped its magnetic judged. but we are still limited by what we can see. Light is a fragile messenger. It gets blocked by dust. It gets scattered by gas. It gets bent by gravity. To truly hear the heart of the giant, we need to stop looking at the light and start listening to the ripples in reality itself. We have measured the scaffold. Now, we are going to listen to the heartbeat. Visual. The screen goes silent. The purple light of the dark matter spike begins to pulse in a rhythmic, deep throb, like a heartbeat in a dark room. Narrator. In Chapter 9, we are going to explore the future of discovery. We are going to move beyond telescopes and into the realm of gravitational waves. We are going to find out what happens when we hear the sound of the universe's most extreme collision. For as long as humans have looked at the stars, we have been limited by a single fragile medium: light. We have used visible light to map the constellations, infrared light to pierce the wall of dust, and radio waves to capture the orange donut of Sagittarius A star. But light is an imperfect messenger. It gets blocked. It gets scattered. It gets bent by the very gravity we are trying to measure. And most importantly, it has a speed limit that keeps us perpetually 26,000 years behind the truth. But there is another way to experience the universe, a way that doesn't rely on photons or seeing at all. Imagine you are in a dark room with a drum. You don't need to see the drum to know it's there. You can feel the vibrations in the floor. You can hear the rhythm. This is the transition we are about to make. We are moving from the era of seeing the invisible giant to the era of hearing its heartbeat. We are entering the realm of gravitational waves. Visual, a 3D model of two black holes spiraling toward each other. Instead of light, they emit glowing, concentric rings of distortion that stretch and compress the grid of space-time. Narrator. In 2015, humanity reached a milestone when the LIGO observatories detected the first gravitational waves, ripples in the fabric of space-time itself, caused by the collision of two distant black holes. But those waves were high-frequency chirps, the sounds of small, stellar mass black holes crashing together in a fraction of a second. Sagittarius A star is different. Because it is so massive, its voice is much deeper. It doesn't chirp. It rumbles. Its heartbeat is a slow, low-frequency throb that our current ground-based detectors are completely deaf to. To hear the heart of our galaxy, we cannot stay on Earth. Our planet is too noisy, too small, and its own seismic tremors drown out the cosmic music. To hear the giant, we have to build a giant. Visual, an animation of the LISA mission. 3 golden spacecraft arranged in a perfect equilateral triangle, floating in the void of space millions of kilometers apart. Laser beams connect them, forming a shimmering, invisible web. Narrator. Enter. LISA, the Laser Interferometer Space Antenna. Scheduled for the 2030s, LISA will not be a telescope in the traditional sense. It will be a triangular array of 3 spacecraft orbiting the Sun and trailing behind the Earth, separated by 2.5 million kilometers. They will be linked by lasers so precise they can detect a change in distance smaller than the width of an atom. LISA is designed to hear the millihertz range, the specific frequency where supermassive black holes like Sagittarius A star live. While the Event Horizon Telescope gave us a snapshot of the ghost's face, LISA will give us a live broadcast of its soul, and what LISA expects to hear is a phenomenon known as an EMRI, an extreme mass ratio in spiral. The spiral tightens and glows brighter as it descends. Narrator. The lore vault of galactic history tells us that the center of the Milky Way is a graveyard. Scattered around our 4 million solar mass giant are hundreds, perhaps thousands, of smaller stellar mass black holes. Every once in a while, one of these smaller monsters gets caught in a terminal grip. It doesn't just fall in, it performs a death spiral. For thousands, or even millions of years, the smaller black hole orbits Sagittarius A star, getting closer with every pass. As it spirals inward, it carves a path through space-time, sending out a continuous rhythmic song of gravitational waves. Because gravitational waves pass through everything, dust, gas, stars, and even the dark matter spike, they carry an unfiltered, perfect record of the geometry near the event horizon. By listening to the pitch and tempo of this spiral, Lisa will be able to map the space around Sagittarius A star with a precision that light can never achieve. Visual. The dark matter spike filaments from Chapter 8 appear. The gravitational wave ripples are seen passing through them. The ripples change shape slightly as they interact with the invisible dark matter mountain. Narrator. This is how we will finally solve the mystery of the dark matter spike. As a small object spirals toward the giant, its song will be subtly altered by the presence of any extra mass. If our black hole is truly wrapped in a mountain of dark matter, the gravitational waves will reflect that. They will tell us exactly how much ghost mass is hidden at the core. We will finally know if Sagittarius A star is a simple, clean, Einsteinian black hole, or if it is a complex, dual structure anchored by an invisible dark matter scaffold. But there's an even deeper mystery that hearing will solve. A gap that the 2022 photo couldn't close: the spin. Visual. The black hole is shown spinning rapidly. The space-time grid around it is twisted like a piece of dough in a mixer. This is frame dragging. Narrator. In Chapter 7, we asked how fast the giant is spinning. Does it rotate at the maximum limit allowed by physics? If it does, it is twisting space-time around it like a cosmic blender, a process called frame dragging. Light from the accretion disk is too chaotic to give us a clear answer on spin, but gravitational waves are different. The spin of the black hole is baked into the ripples it sends out. When Lisa hears a small black hole fall into our giant, the wave pattern will shift and wobble in a specific way that reveals the exact rotation speed of those 4 million suns. If Sagittarius A star is spinning at near-light speeds, it means it is a massive reservoir of rotational energy. It means the magnetic mayhem we saw in Chapter 6 is being powered by the very rotation of space itself. We would be orbiting a space-time engine of unimaginable power. Visual. The fuzzball model from Chapter 7 reappears. The gravitational waves are shown bouncing off its surface, creating a delay or an echo. Narrator. And then, there is the ultimate unanswered question, the one that keeps theoretical physicists awake at night. Does the event horizon have a surface? Standard general relativity says the horizon is a mathematical line, a nothing that you pass through. But alternative theories, like the fuzzball or gravistar models, suggest that there might be a physical structure at the edge. If Sagittarius A star has a hard or fuzzy surface, gravitational waves might actually echo. When a small object falls in, the ripples might bounce back off the interior structure, creating a faint secondary signal, a gravitational echo. If Lisa detects even a single one of these echoes, Einstein's greatest theory will have to be rewritten. We would have proof that the invisible giant isn't a hole in the universe, but a new state of matter entirely. Visual. The camera pulls back, showing the Lisa triangle once more, set against the backdrop of the entire Milky Way. The heartbeat sound is now clear, steady, and dominant. Narrator. For 26,000 years, the light from the center has traveled to us, only to be blurred and dimmed by the obstacles of the galaxy. We have been like people trying to read a book through a thick fog. But gravitational waves don't care about the fog. They are the heartbeat of the galaxy, and they have been washing over the Earth since before the first humans walked the plains of Africa. We just haven't had the ears to hear them. With Lisa, we are finally opening our ears. We are preparing to listen to the final moments of stars, the rotation of the abyss, and the secret geometry of dark matter. We are moving from a world of shadows to a world of sound. Visual. The screen begins to fade to a deep cosmic purple. The heartbeat slows down, becoming a heavy, resonant thud. Narrator. But there is one final sound that Lisa is waiting for. A sound that will be so loud it will shake every atom in our galaxy. It is a sound that isn't happening now, but is an absolute certainty for our future. It is the sound of the collision that will end the Milky Way as we know it. In our final chapter, we are looking forward. We are going to witness the end of the invisible giant and its rebirth into something far more terrifying. We have spent this journey exploring a ghost, an invisible anchor that has held our galaxy together for billions of years. We have seen Sagittarius A star through radio eyes, watched its stellar ballet, and felt the ripples of its magnetic mayhem. But even for a supermassive black hole, time is not a circle. It is an arrow. And that arrow is pointing toward a definitive cataclysmic conclusion. Right now, as you sit here, our galaxy is on a collision course. Deep in the local group of galaxies, the Andromeda Galaxy, a titan larger than our own, is falling toward us at 110 kilometers per second. To a human, that speed is incomprehensible. To the universe, it is a slow, inevitable drift. In approximately 4 billion years, the invisible giant at our center will finally meet its match. This is the Andromeda Countdown. It is the story of how our quiet, selective feeder wakes up to become the most violent object in the local universe. Visual, a wide-scale simulation of the two galaxies approaching. Wisps of gas begin to bridge the gap between them, glowing orange as they are compressed. Narrator. When people hear the word collision, they imagine a car crash, metal twisting, stars smashing into one another. But space is mostly empty. When the Milky Way and Andromeda finally meet, almost none of the 400 billion stars involved will ever touch. They are like grains of sand separated by miles of desert. The real collision isn't between stars. It's between the invisible forces we've spent this documentary hunting. It is a collision of gas, of magnetic fields, and most importantly, a collision of the two dark matter spikes that anchor our respective homes. As the galaxies begin their first pass, the wall of dust we explored in Chapter 2 will be shredded. The massive clouds of hydrogen that have remained relatively stable for eons will be funneled toward the center. This is where the lower gap of the selective feeder finally closes. The magnetic shield we discussed in Chapter 6 is suddenly overwhelmed by a colossal influx of gas. The mouth of the giant finally opens. Narrator. For millions of years, Sagittarius A has lived on a starvation diet, its magnetic fields acting as a shield to push matter away. But the Andromeda merger will provide a feast so massive that no shield can hold it back. Millions of solar masses of gas will be funneled into the galactic core. The quiet giant will roar to life. Sagittarius A star will transform into a quasar, a blazing beacon of radiation that will outshine the rest of the galaxy combined. Relativistic jets, which we found absent in the 2022 photo, will finally erupt from the poles, screaming across 50,000 light-years of space. These jets will act as a cosmic blowtorch, clearing out the gas and halting star formation across the new, merged core. But the true drama is happening even deeper. And Andromeda's M31, beginning to orbit each other. They are caught in a purple-tinted web of dark matter. Narrator. While the stars are being rearranged into a new, giant, elliptical galaxy we call Milky, the two central black holes will begin a process called dynamical friction. This is where the dark matter spike we investigated in Chapter 8 becomes the main character of the story. As Sagittarius A star and Andromeda's black hole, M31 star, move through the dense fog of stars and dark matter at the center, they leave a wake behind them, a trail of gravity that pulls on them, robbing them of momentum. Think of it like a boat moving through thick honey. The honey slows the boat down, dragging it toward the center of the pot. Over millions of years, the dark matter spike acts as the ultimate cosmic drag, forcing the two black holes to spiral inward toward each other. Visual. The two black holes are now only light years apart. The space between them is a distorted mess of gravitational waves, shown as concentric ripples. Narrator. They will begin a death spiral that will last for eons. If the Lisa mission we discussed in Chapter 9 were still listening, it would hear a song of gravitational waves so loud that it would drown out every other sound in the universe. Andromeda's black hole is significantly more massive than our own, estimated at 150 million solar masses. Compared to it, Sagittarius A star is the junior partner. But as they merge, they will not just add their masses together. They will undergo a fundamental transformation of internal physics. This brings us back to the information paradox. If these two fuzzballs of energy, these two seeds of potential new universes collide, what happens to the information they contain? Theoretical models suggest that in the final milliseconds of the merger, the event horizons will touch and ring like a massive cosmic bell. In that instant, a significant fraction of their combined mass, the equivalent of several entire suns, will be converted into pure gravitational energy and radiated away into the void. It is the most efficient explosion possible in physics. Visual. A blinding flash of light as the two event horizons become one. The resulting black hole is a titan, surrounded by a calm, massive accretion disk. Narrator. The result will be a new, singular titan, a supermassive black hole with a mass approaching 100 million suns. The invisible giant we have known as our anchor will be gone, replaced by a much larger, more powerful descendant. But what about us? What about the Earth and the Sun? By the time this merger reaches its climax, our Sun will have already begun its own transformation into a red giant, likely scorching the Earth into a lifeless husk. But the gravitational chaos of the merger could provide a final twist. The Sun could be flung out into the far suburbs of Milky Way, or it could be pulled into the dense radioactive core of the new galaxy. Visual. The camera pulls back to show the final result. Milky Way, a giant glowing elliptical galaxy with no spiral arms, just a smooth golden glow. Narrator. We are always watching the past when we look at Sagittarius A star. We see it as it was 26,000 years ago. But by studying its selective feeding, its dark matter spike, and its magnetic mayhem, we are actually reading the blueprints of our future. The invisible giant is not just a hole in the map. It is the clock by which our galaxy lives. It held us together through the Ice Age, watched as we built our first cities, and stood by as we finally turned our radio telescopes toward the stars. One day, the countdown will hit 0. The Milky Way will change, the giant will wake up, and the story of our home will reach its final brilliant chapter. You have been moving your entire life. Now you know where you are going.